Okay, good morning students. So today is 1st of May and today we will be doing Rolle's Theorem, okay? And this Rolle's Theorem is very important for your ISC, as every year the question is coming from Rolle's Theorem. It carries a 4 marks, okay? So let's understand Rolle's Theorem first. So the statement of Rolle's Theorem is, if a function f, okay, if a function f is, there are three conditions now. If a function f is, number one, if the function f is continuous in closed interval a comma b. Now if this function f is continuous in closed interval a comma b. Number two, if the function f is derivable in open interval a comma b. These are the two conditions: closed a comma b, open a comma b. Okay, number three is if the value for f at a and if the value for f of b are equal. Okay, so three conditions are there. Rolle's theorem states that if f is continuous in closed interval a comma b and derivable in open interval a comma b, and if f of a equals to f of b, then Rolle's theorem states that there exists at least one real number c. Now there's a question mark. This is actually, there's an error. Okay, c belongs to open interval a comma b. Then Rolle's theorem states that there exists at least one real number c which belongs to open interval a comma b, such that f dash of c equals to 0. So this is the statement of Rolle's theorem. Now the question, you might not be clear with the statement. Once we do the exercise, you'll be clear with this. Okay, but once again the statement, you have to go through it. If the function f is continuous, if the function f is continuous in closed interval a comma b. Number two, if it is derivable in open interval a comma b. Number three, if f of a equals to f of b, then Rolle's theorem states that there exists at least one real number c which belongs to open interval a comma b, such that f dash of c equals to 0. Please refer to your book as well. Now we will understand what do we mean by closed and open interval. What do you mean by this is closed interval and this is open interval? Okay, so what do we mean by closed interval? Now closed interval means if any value belongs to closed interval belongs to closed interval a comma b, it means that either x can take the value a, either x can take the value b, or in any value in between a and b. So that's why I've written out here a less than equals to x less than equals to b. X can be either a, x can be either b, or any value in between a and b. But if we have open interval, then x cannot take the value a and b. It can only take the value in between a and b. So the basic difference between closed and open interval means in closed interval, in closed interval, x can take the value, the extreme values as well as in between, but in open interval x can only take the values in between. It cannot take the extreme values. So hence this is your Rolle's theorem. Okay, so now we'll look at the sums and the applications of Rolle's theorem. Okay, so first we are taking is the first example. Okay, so before that, note how to verify Rolle's theorem. Okay, remember that algebraic, exponential, inverse, trigonometric, logarithmic functions are all continuous and derivable. We don't have to check. Okay, it is automatic by default. They will be continuous as well as they are differentiable. So when we do the sums, we just have to write as the function is algebraic, it is continuous as well as differentiable. So the first and the second condition is already satisfied. Okay, so when we verify Rolle's theorem for a given function in the given interval, then we simply start from point number 3. Then point number 3, f of a equals to f of b. Okay, stating that point number 1 and point number 2 are already satisfied by the function. Okay, so we check if f of a is equals to f of b or not. That's the third point. And then we find f dash of x and f dash of c. Remember that we are finding c, and for Rolle's theorem f dash of c is equals to 0. Then we find that whether c is belonging in the range open interval a comma b or not, because according to the theorem there exists at least one real number c which must belong to open interval a comma b. Okay, so these are the points that we need to remember before solving problems on Rolle's theorem. Okay, number one, these are continuous and derivable. Number two, we start from number 3, condition number 3. Okay, after that we're checking f of a equals to f of b or not, and then we find f dash of x, f dash of c, and we equate equals to 0, and we find the value for c. Okay, so let's take now question on Rolle's theorem. Okay, so this is an example which I have taken from the book. The question is, verify Rolle's theorem for this function fx, which is equals to x squared plus x minus 6. The question is, verify Rolle's theorem where fx equals to x squared minus x minus 6. So what type of function is it? It is not a trigonometric, it is not exponential logarithm, but it is a polynomial function, and we know that polynomial function is always continuous and differentiable, and we need to verify this function, this polynomial function, in closed interval -3, 2. So remember that -3 is the value for a and 2 is the value for b. So we need to verify Rolle's theorem, which means we need to find the value for c, which must belong in the open interval -3, 2. Okay, whatever we find, the value for c must belong to open interval. Huh? Don't get confused, here it is closed interval, but when we find the value, it must belong to open interval -3, 2. So let's see the solution. Okay, so as the given function is a polynomial function, number 1, f is continuous in closed interval a comma b, and number 2, f is derivable in open interval -3, 2. Okay, because it is a polynomial function, it is always continuous and differentiable. Okay, okay, so now we go through point number 3, whether the value for f of a and f of b are equal or not. Fx is given to us x squared plus x minus 6. So we find f of -3 and f of 2. We know how to do it. Just put the value for x equals to -3 and put the value for x equals to 2. Then we check the values. It should be equal. Okay, so here is the value for f of -3. So f of -3, wherever it is x, you put x equals to, wherever it is x, you put x equals to -3. So -3, sorry, there's a missing whole square, but it is -3 whole square, -3 and -6. So -3 whole square will be 9. I'm showing the next step. Okay, so -3 whole square is 9, and then -3 and -6. So hence we get -3 minus 9 minus 3 is 6, and 6 minus 6, which will be 0. So hence the value for f of -3 will be 0, as well as you find the value for f of 2. This is 2 whole square. Your whole square is missing out here. Please be careful with this. 2 square, 4 plus 2, 6, 6 minus 6, 0. So hence we got f of -3 equals to f of 2. So which means that f of a equals to f of b. So number 1, it is continuous. Number 2, it is derivable. Number 3, we also got the value for f of -3 equals to f of 2. So hence all the 3 conditions of Rolle's theorems are satisfied. Therefore, once all these 3 conditions are satisfied, it states that there exists at least one real number c which belongs to open interval -3, 2, such that f dash of c equals to 0. Now our main intention is to find the value for c. All the 3 conditions are satisfied. This was the third condition. There exists one real number c which belongs to -3, 2, such that f dash of c equals to 0. So our main intention is to find the value for c. And how will I find? Finding f dash of x and find f dash of c equate equals to 0, will get the answer. Okay, now we know that f of x equals to x squared plus x minus 6. So can we find f dash of x? Okay, so differentiating both sides with respect to x, we get f dash of x will be 2x plus 1. Very easy. And f dash of c will be 2c plus 1. Just substituting the value for x equals to c. And now we know that, once we found this, we know that f dash of c equals to 0. So just equate this value is equals to 0. Therefore, for Rolle's theorem, for RT means for Rolle's theorem, f dash of c equals to 0. So when you put c equals to c, when you put the value for f dash of c from here, f dash of c equals to 2c plus 1. So 2c plus 1 equals to 0. So c equals to minus half. So we are getting c equals to minus half, which is minus 0.5. So what does it imply? C is equals to minus 0.5. It's missing out here. Please rectify it. C equals to 0.5. Does it belongs to open interval a comma b minus 3 comma 2? Obviously, yes. It does belongs. C equals to minus 3 comma 2. C equals to minus 0.5. It belongs to open interval minus 3 comma 2. So I hope you are clear. Minus 3 comma 2. I hope you can imagine minus 3 comma 2. So minus 3, minus 2, minus 1, and then we get minus 0.5. So it is in the range this. So hence RT is verified for the function f(x). Okay, so this is how we have to solve problem on Rolle's theorem. And now we check another question. This is from exercise 5.14. Verify Rolle's theorem. A similar type of question is given to us. Okay, so I hope you're now clear how to proceed. See, f(x), again it is a polynomial function. We have to check in closed interval 1 comma 4. The value for a is 1 and the value for b is 4. Okay, so here f(x) is a polynomial function. f(x) is continuous. We know all the polynomial functions are continuous in closed, derivable in open. So we start with point number 3. Find the value for f of 1. Wherever it is x, you put 1 square minus 5 into 1 plus 6. So I've done out here. We get f of 1 equals to 2. Please check it. F of 4, again we get f of 4 also equals to 2. So therefore f of 1 equals to f of 4. As all the three conditions of Rolle's theorems are satisfied, therefore Rolle's theorem states that there exists at least one real number c which must belong to open interval a comma b, that is 1 comma 4, such that f dash of c equals to 0. So we start with the third one then. As f of x is equals to x square minus 5x plus 4, f dash of x will be 2x minus 5. And f dash of c will be 2c minus 5. Again we know that f dash of c equals to 0. So 2c minus 5 equals to 0. And then c equals to 5 by 2. So c is 2.5, which is belonging in the open interval 1 comma 4. So hence RT is verified. So in the same way you will do question number 1 part 3. You will do question number 1 part 3, 2 part 1, 2 part 3. Okay, do take the help from examples from your book and then solve this using Rolle's theorem. Okay, so that's it for today. I'll see you in the next one.